Hello everyone, myself Dr. Sriparna Shah, and currently we are discussing about artificial intelligence. So far we have talked about different search techniques up to the heuristic one. Today we are going to talk about the classical, that is the beyond classical search techniques. So let's start today's lecture. So the beyond classical search. So why to go beyond? What we have talked about so far, that is the earlier search strategies, there are some constant parameters are there, that is the environment should be observable, deterministic and known. If these constants are satisfied, then only those type of problems can be solved by the classical search technique. But suppose if your environment becomes unobservable, or it's not deterministic, or it's unknown, then the earlier search strategies or techniques are not applicable in those particular problems. So, in the earlier search techniques, what the result we have got after the search techniques, that is, we have got a solution that is a sequence of action. What is that? Suppose this is your start state S and you need to move to the goal state, that is the G. What you need to do? You need to find the path, right? That is, from S you need to go to the C state, then F, then H, then G. So we need to, in the breadth first search or depth first search or other search strategies, or the A-star search or any other classical search strategies, what we have talked, that is, I have in one particular state we need to go to the goal state and we are concentrating on the path, that is, what are the sequence of actions you need to take to reach the goal state, and we have concentrated on the intermediate states as well. But now we are not going to concentrate on the state, those are in between the start state and the goal state. But in this particular search algorithm that we are going to discuss today, there the path is irrelevant. That is, in the many optimization problems, the path to the goal is irrelevant. The goal state itself is the solution. We need to reach one particular point, but how we are reaching that particular point, that is not our constraint, or we are not concentrating on that point. We are not concentrating on the path. We are just concentrating to reach the goal state. Okay, so here what we need to define, we need to define a state space, and that is the set of complete configuration, and we need to find the configuration that satisfying the constraints. For example, we are going to talk about these local search algorithms in terms of n-quiz problem that we are going to come in the later slide. So in these search cases, we can use the local search algorithm. And these local search algorithms keep a single current state and tries to improve it. That is, we are not concentrating in the path, that is the intermediate state. The goal state itself is our solution. So the n-quiz problem. So what was the problem? That is, you need to put n queens on an n cross n board with no two queens on the same row, column or diagonal way. That is, if this is suppose your start state and this is suppose your goal state, you need to move from the start state to the goal state. And what are the intermediate state that you are traversing? That is none of your concern. You should not bother about that. But you need to just read the goal state. That is the local search technique. So in this type of search techniques, we have the concept of optimization. That is, we need to optimize the certain value of one particular state. As we have already talked about, the local search algorithms keep track of single current state and move only to neighboring states, and it ignores the path in between that. So what are the advantages? As we are only keeping track of one single state, so it's going to use a very little amount of memory, and it can often find reasonable solutions in large or infinite, that is the continuous state spaces. If the particular local search algorithm is a pure optimization problem, then all states have an objective function, and our goal is to find a state with maximum or minimum objective value. This type of problems does not require or does not quite fit into path cost or goal state formulation. They do not have that particular logic of path cost or goal state that we have talked about in the earlier A-star search algorithm. But here we have the concept of objective function, and we need to optimize that objective function to reach the maximum or the minimum value. And this local search can do quite well in this type of problems where we need to optimize one particular objective function of the problem. So here what we need to define? We need to define a state space. So this state space basically looks like a this type of figure. Here the objective function is along the y-axis and the state space, that is which state the values, that is along the x-axis. And this particular figure is a landscape for the state space. So a landscape has both location, that is defined by the state, and elevation, that is defined by the value of the heuristic cost function or objective function. So this particular landscape suppose looks like this. So it has different parameters. What is the global maxima, local maxima, that we are going to talk about now. So as from the figure you can see, that is, suppose it looks like something like a mountain, right? In this particular sort of thing, there are different peaks are available. One peak is highest among all the other peaks. So that is the global maxima. Suppose this problem is to find the maximum value for the objective function for one particular state, and that state will be our goal state. So we need to reach the global maxima one. So this is your global maximum. Now there are several other peaks, but those are lower in height than the global one. So those are known as local maxima. There, suppose you are in this particular position, this is your current state. What will be your aim? Your aim will be reach to the maxima point. But suppose you are in this point, you are trying to reach the maxima point. In which direction you are going to go? We are going to go in this direction, right? Okay, sorry. So this direction you are going to go. So you are going to move in this particular direction. So then this direction, then you will be reaching is this particular point, that is the local maxima point. But after local maxima point, reaching that particular point, what you are going to do? You cannot go in this particular direction, as it will be the lowering of the objective function. So you will not go in this direction, will be only staying at that particular position. But now we have came to the local maxima one, but your aim should be reaching the global maxima, that we cannot reach. So that is the one particular problem of this type of local search algorithm. You might trapped into the local maxima. So this is the concept of local and global maxima. Now let's move to the hill climbing search or steepest ascent version. Why this name is hill climbing? So this figure is there. So what we are trying to reach? We are trying to reach the global maxima point. So if you are trying to reach the maximum point, so you are just rising up the mountain as you are climbing the hill. So this type of problem is known as hill climbing search. Another name is steepest ascent version. So here a loop that continuously moves towards increasing value, and it's going to terminate when a peak is reached. These type of algorithms are also known as greedy local search. Now the value that we are going to concentrate, that can be either an objective function value or a heuristic function value, that is the minimized version. Hill climbing does not look ahead of the intermediate neighbors. So hill climbing does not look ahead of immediate neighbor. What does that mean? So that is, you might trapped into the local maxima. So what is this neighboring state? Is this neighboring state, right? So it knows that one is downside in the objective function, another is the upside of the objective function. So what direction I should go? I should go towards the upward or the hill, climbing the hill way towards. But what it does finally, it's going to trap at the local one, right? Local maxima point. So it's not thinking beyond the neighboring state. So it is never going to go to the global maxima one if it's following the hill climbing search. And our aim is to reach the global maxima, not the local maxima. So that is, hill climbing does not look ahead of immediate neighbor, and it can randomly choose among the set of best successors if multiple have best value. So if there are suppose two neighboring state and both have the same value, so it can choose among them randomly. So as it might going to take you to the local one rather than the global one, so you might trap at that. So this type of search technique is also known as climbing Mount Everest in a thick fog with amnesia. That's the one thing that you can understand from this, that what could be the problem of this hill climbing search. So let us talk about this particular search technique in the n-queen problem. So what is the state in the n-queens problem? That is the position of all 8 queens on the board, right? That is the configuration. Now what will be the successor function? That is move a single queen to another square in the same column. That is the successor function. And what is the heuristic cost function over here? That is the number of pairs of queens that are attacking each other, either directly or indirectly. And in this particular figure, if you calculate that is the number of attacks or the heuristic cost function, you are going to find the h value is equal to 17. How? I'm just giving you some example that it is attacking this directly, but it is attacking this indirectly. Similarly, you need to calculate how many attacks are there for each of the queen. Then you are going to get this particular state has the h value of 17. And what we try to get here, we need to try to minimize this value. So we need to go to one particular state where none of the queens are attacking each other. If none of the queens are attacking each other, the h value should be 0. So that is, for the heuristic cost function, we need to go to the global minimum of this function. That is why it has been told that is when we need to find out the minimum value, that is the heuristic function value we need to calculate. So this is the 8 queens problem. So as the drawbacks, so we have already talked about the drawback. One drawback is we might trap at the local maxima. Another is the plateau. The plateau is a flat area. It can be a flat local maxima from which no uphill exists, or a shoulder from which progress is possible. So it might this particular thing where neither you can go to the global maxima, there is no way, and it can be a shoulder as well, where after traveling to a certain number of neighboring states, you can find the path to reaching to the global maxima. That is the plateau. And it's the ridges. So these result in a sequence of local maxima that is very difficult for greedy algorithms to navigate. So this is the example. This is this type of state space can be. This is a sequence of local maxima. See, this is the local maxima, then this is local maxima, this is local maxima. So there are several local maxima points available. So it is very difficult. So these are the drawbacks. Now, to escape the shoulders or the sideways move. So, in the plateau, there can be two types. One is the flat area, where the solution is not possible by the hill climbing approach. But another of the plateau is the shoulder. From the shoulder, you can go beyond and reach the global maxima. So, what we can do to escape the shoulder? We can move sideways. That is, if no downhill or uphill moves, that is, if we are going for the maxima or the minimum one, so that is the downhill and uphill both has been considered. Allow sideways moves in hope that algorithm can escape. So suppose you have reached one particular point. Suppose you have reached here. So it finds that the neighboring state both have the same value of the objective function, but it's going to traverse some much more point in the hope that it might, after reaching a certain point, that is this point, it might find the uphill move. So that is the thing, that is you are going to allow sideways moves in hope that algorithm can escape. That was the logic. Now need to place a limit on the possible number of sideways moves to avoid infinite loops. So how many number of sideways move you can go? So that you need to find a limit. So suppose in the n queens problem, suppose we are allowing the sideways moves, the limit is 100. So then the percentage of successing the problem or to find the solution of the problem becomes 14 to 94%. So if we allow a sideways move with a limit of 100, the percentage of getting success is raised in this way. This is the how to find the solution if you are trapped at the shoulder. Now, there are certain other problems that we have already talked about. That is the major problem of the hill climbing or the greedy search algorithm version of it is that it might trapped at the local one rather than at the global one. So, if you trapped at the local position, how to move to the global one? So, in the stochastic hill climbing, random selection among the uphill moves. You need to randomly select another point, and the selection probability can vary with the steepness of the uphill move. So suppose you are trapped at the local one. So you are trapped over here, local maxima. What you can do, you can randomly move to another state and check whether reaching the random state you are again coming to the local maxima or the global maxima. Suppose you are in this point. So for you it becomes that this is the global one. Why? From here no other uphill moves are possible. So you understand. So I have reached my goal. So what you can do? You can randomly select another state. Suppose you are randomly selecting this point. So what happens now? If you are randomly selecting this point, you are going to uphill move. So you are going to reach this particular position. Now you are checking whether this position objective value is greater than this position value. Answer is no. So earlier you must have reached at the local one. Now you might reach the global one. So that is, you can randomly restart the algorithm. So that is the random restart. So this is the randomly selecting another particular state. Now to avoid getting stuck at local minima, there are some variations in the hill climbing. So there are three types of the random restart hill climbing, random walk hill climbing, and hill climbing with both. That is random restart and random walk both at the same time you are doing for the hill climbing process. So hill climbing with random restart. So if at first you don't succeed, what you should do? You should try and try again. So that is the different variations are there, and for each restart, run until termination versus run for a fixed time. Run a fixed number of restarts or run indefinitely. Now what is the analysis you can do? That is, say each search has probability P of success. So for 8 queens, P is equal to 0.14 with no sideways moves. Now there are two things you need to decide before starting this random restart problem. That is, what is the expected number of restarts? That is, how many times you are going to restarting the thing. That is, you cannot go for the infinite one, right? You need to identify one particular time you are going to will be restarting the algorithm, and you need to, another constant is that you need to understand before doing, or you need to specify that before running this particular algorithm, that is the expected number of steps taken. How many number of steps we are going to take to reach the global one. So these type of two parameters you need to decide before running this algorithm. And if you want to pick one local search algorithm, then you should learn this particular one. That is the hill climbing with random restart. Another one is what? Hill climbing with random walk. So what is that? You are in one particular state, you are randomly walking. So I know that I am going towards the down of the hill, but again I am doing it. So what you can find over here, you might find the global one. So just let me give you the example. Suppose this is the hill, right? Now you are in this particular position. Sorry, you are not in this particular position. Just a second. Right. So now suppose you are in this particular position. So what you can do? You can will go to the field, right? But random walk means you are not moving over there. You are randomly starting moving over here. Then you find, yes, there is another hill way. So you can reach the global one by randomly walking. Okay. So this is the random walk. It has two variations. One is the greedy, another one is the random. So greedy with probability P move to the neighbor with largest value, and for the random one with probability 1 minus P move to the random neighbor. These are the two variations. And the last variation on the hill climbing, that is including random. It is that a random one. So what we can do, that each step, that is at each step do one of the three. That is, first is the greedy, that is a move to the neighbor with largest value, right? That is the first of that is the basic hill climbing approach. Then the random walk, that is move to a random neighbor, and random restart, resample to a new altogether new current state. Not the neighbor, but altogether new current state. You are starting your algorithm from there. So these are the three variations, and accumulating both of the all of the three variations is hill climbing with both algorithm walk. So this is the now let us move to the simulated annealing process. So in your science class, you must recall that particular word called annealing. So annealing is a physical process of cooling a liquid or metal until particles achieve a certain frozen crystal state. By taking that annealing process of the physics, we have designed this search technique, that is the simulated annealing. So here the free variables are like particles, and they all seek to go to the low energy or high quality configuration. And what it does, that is slowly reducing temperature T with particles moving around randomly. By that, take the physical analogy, that is imagine letting a ball roll down on the function surface. So this is the function surface. You are imagining that you are rolling the ball down towards this. This is like the hill climbing for minimization, right? Considering the minimization concept. Now imagine taking the surface while the ball rolls and gradually reducing the amount of shaking. This is like the simulated annealing. So you are rolling the ball towards this position, at the same time you are shaking the surface. Now as you are shaking the surface and you are reducing the shaking each timestamp by each timestamp, then it is this type of process is very much analogous with the simulated annealing. So then the name came simulated annealing. So suppose this is your initial position. Suppose this is the initial position of the ball. Now what happens in this initial position of the ball? The greedy algorithms, if we apply the greedy algorithm, it might take you to this particular position. So the greedy algorithm is not the solution over here, but you can solve the problem with the simulated annealing. As if you are going for the greedy algorithm, this is your ball position. What happens now? Both of the side is the uphill move, and right now we are moving towards the minima position, right? We are finding the local minima actually. Here in this particular thing, we are going for the local minima. We are going forward the local minima. So as you are in this particular position, both of the side the objective function is higher, and you are trying to reach the minima point. So you are not going to move to these two sides. But if it's a simulated annealing, it is going to shake the surface. So it is explores more, so it might take the ball towards this position or this position. So if it move towards this position, so then it might reach you to the this position, and it might take you to there. Then from here there is a certainty will reach to the global minima. So upon a large number of iteration, the simulated annealing, that is the SA, converges to the solution. So this is the convergence of the problem to reach the global minima. So we need to reach the global minima over here, and this is your global minima, right? So in the simulated annealing, by shaking the surface, you might take the ball to from here to here, and if it reach over here, it might takes you down over here, that is the global position. So here the idea that we have already talked about, that is to escape the local maxima by allowing some bad moves but gradually decreasing their frequency. So we are doing some bad moves. We know that we are doing some bad moves, but we are gradually decreasing the bad moves, and our aim is to reach the global one. This is the simulated annealing. Apart from that, there is another search technique, that is the local beam search. Here, the idea is to keeping only one node in memory is an extreme reduction of memory problem. So, in the earlier search techniques, what we are concentrating, we are keeping track of only one particular neighboring state, or one particular, if it's a random restart, then one particular state randomly chosen. We are not considering all the other state that you have already traversed. So that is that only one particular node, information of that particular node is okay to have a very less amount of memory consumption. But sometimes the problem might not be solved by that. So in the local beam search, what we do, we keep track of k states instead of one. So that is, we are initialize the particular algorithm with k randomly selected states. K randomly selected states have been chosen, and next we are going to determine all successors of k states. And if any of the successor is goal, the algorithm is going to terminate. Else, best, we are going to select the k best from successors and repeat. So not only one particular state, but we are going to keep track of k number of states at the same time. So here the memory consumption will be much more higher, but success also, rate of success is also getting higher. So this is the local beam search. So not the same as k random start. Here in the k random start, what happens, we are randomly starting the algorithm. That's okay, but there also you are going to keep track of one particular state. But here k number of random start are going to run parallelly for the local beam search, and it searches that find good states and recruit other searches to join them. Here can be one problem, that quite often all k states end up on same local hill, that is, we might reach the local position, not the global one. Now the idea is the stochastic beam search, that is, choose k successors randomly and bias towards good ones. And this very much observes the close analogy to natural selection process. So this is the local beam search. Now last type of is the genetic algorithm. For this genetic algorithm, I am not going to talk about this particular in this particular lecture series. As for the genetic algorithm, I have a altogether lecture videos that are already been uploaded in the YouTube. So you might go to in here, there the genetic algorithms, all the videos are there. And if you want to know very brief about the genetic algorithm, then the first video is enough for you. But you want to go to the deeper of the genetic algorithm, you might look all the videos to know all the details about the genetic algorithm. So this much for today, that is the beyond classical search topic. So thank you everyone for watching this particular video, and happy studying.